do. Ruth Wunderlich will be talking to us about, what is it?
What to do
Regression,
when there's too much
information, regression towards the mean.
Okay, we don't have a lot of people in here, and what we're gonna, this is statistics, right? Statistics about collecting data. And if you know anything about statistics, you know it's a numbers game. So it's not very useful to collect data from 2 or 3 people. You want to collect from a group, because it's about what happens when there's a bunch, right? So I'm a little nervous because the first thing we're going to do is we're going to collect some data, and we don't have tons of people. So if any of you feel like being 2 people, that's just fine with me. That's just fine with me. Okay, so does everybody have a handout? You're going to need the handout, and you're going to need something to write with.
Does anyone not have it? Just raise your hand if you don't have a handout.
I need every single individual here to do this, because we're short on numbers right now, so we really need to get everyone to do it.
There you go.
Is your dad going to do it? You get him a handout. You keep them on it. Okay, and you're welcome to be 2 people, because if we really want to collect a little bit of data, so that would be cool. Okay, what I'm going to do is I'm going to give you a test, as you can see, and you're going to have to turn it in, so you can just rip it right off. So you have it. And before I start, I'm going to say just a little bit about statistics and collecting data. So the first thing is, if you're going to study statistics, you need to look at data and see how real data behaves. So that's partly why we're collecting data, is because, thank you, I really appreciate that. What's your name? Paul, thank you. When you collect data, when you study statistics, you need to study data, and you want to study real data, what real data acts like. So that's partly why we're collecting data. So one of the problems that comes up is that you don't want your data to be bad. And the best way to collect data is usually to get everybody to do something, right? If everybody does, if someone or 2 or just a couple few people in the room decide not to do it the way it's supposed to be done, that can mess up your whole data set. So it's really important that everybody follows the instructions, because you don't just mess up your stuff when you don't follow the instructions. You mess up everybody. It's like so many things in life, right? Not doing what you're supposed to do can have an effect on everybody else, and that's really true. So it's really important that everybody follows the procedures that we set forth. So I'm going to make you promise that you're going to do that. Also, this is going to be not completely serious, what we're about to do. And I need you all to promise that no matter what happens, you will play along. So raise your right hand. Repeat after me. No matter what happens, I will play along. And I will follow the procedures. Okay. Now you've all promised. Okay, so the first thing we're going to do is take this test. You'll notice that I failed to give you any questions or any answers. But I need you just to select one answer for each of these 10 questions. Do it right now. This is a hard test, I know, but it's also time. You've got 1 minute. Okay, so look around you, make sure everybody around you has filled out their, not the retest, don't take the retest, not yet. Just the test. Just the test. See, retests happen later, if you think about what it means. Just the test, 10 questions, 10 answers. Look at the people around you, make sure that everybody has filled it out. I don't want any cheers. your name up at the top or initials or something up there. Okay. I'm being patient because I want to make sure we get some more data. I want the new people to have a chance. If you just got here, what you need to do is select 10 answers, A through D, on that very top sheet. Just do it nice and quickly. No stress. Okay. Okay, has everybody selected their answers?
Yeah.
Now we're going to grade them. Okay? And this is kind of a funny test because it turns out that there's only one way, in each problem there's only one way to get it wrong. There's only one way. So that's kind of nice, right? So here's the key, and I'll read the answers to you so it'll be easy for you to grade. So I'm going to read off. So for example, on number 1, if you circled A, you got to mark that one wrong. Otherwise, you got it right. Does that make sense?
Okay.
So I'm going to read them off, and you can go ahead and mark the ones wrong that are wrong, okay? So 1, A is wrong. Mark it wrong if you put A. 2, C is wrong. Mark it wrong if you put C. 3, D is wrong. Mark it wrong if you put D. 4, A is wrong. Mark it wrong if you got A. Number 5, C is wrong. Mark it wrong if you put C. Number 6, A is wrong. Mark it wrong if you put A. Number 7, C is wrong. Mark it wrong if you put C. Number 8, A is wrong. Mark it wrong if you put A. Number 9, A is wrong again. Mark it wrong if you put A. And number 10, B is wrong. Okay, so everybody has graded their test. Now I want to record how we all did. So the most you could get on this test was 10, right? Anybody get 10? One person? And then who got 9? 1, 2, 3. It figures you would. That's my son over there. Even when it's pure luck, that's what he does. Okay. So if you got a 9 or 10, I think that's a pretty good score, right?
Wait, I need to do.
Okay, I'll leave that up there for you. Okay, so if you got a 9 or a 10, what I want you to do up at the top of your test, I want you to write good work. What about 8? You got 8. 1, 2, 3, 4, 5, 6. I see.
You forgot me.
7.
I got 8 on this one too.
Now, is that right? I got them wrong? 7. Who got 7? 1, 2, 3, 4, 6, 7, 8, 9. Yeah, you were trying to do 2 at once. I see why that was hard. I said 9, right? Okay. Okay, so I think those are decent scores. Don't you? If you got a 7 or an 8, I want you to put a check at the top of your. Okay? 6. 1, 2, just 2. 5. No 5s? 4. 1. Any 3s, 2s, or 1s? That's all of us? Okay. Okay, so if you've got a 6, a 5, or a 4, I want you to write at the top of your paper, please see me. Okay. So what we're going to do, of course, is the people who have to come see me, and I really mean it, you do need to come up here and see me. The people who got those low scores, I'm going to just have a discussion with them because I want them to improve because, of course, that's not the way I want them to do better on the test, right? So I'm going to have a little discussion with them. But while you got the rest of you who did fine on the test and are not worried about you, I know you know the material. I'm going to have you take a peek at the very first page of that handout. Statisticians always check their assumptions. That's one of the things we do. And there are a few assumptions I have about things that you already know about in order to listen to this presentation. And they're at the bottom of that first page. You see them there, assumptions. There's 4 things. So my assumption is that you know something about all of that. So I want you to actually look at it and decide if you know about it and what you know about it. And if you don't know about one of the things down there, maybe like talk to your neighbor, see if they know about it and can explain it to you. Okay, so that's what you guys are all doing. All you guys who did plenty well on the test, that's what you're doing. And then you guys down here, come see me, please.
Were there any questions about it?
Sorry, you have to go down.
We'll meet on that. We'll meet you over here. Okay. Okay. In just a moment, I'm going to check with you on those assumptions, and if there's anything you really want to ask me about those things, I'll be happy to talk about them. Okay, so we'll get back to that in a moment. But I have now met with the students who didn't do so well on the first test here. And I have every confidence that they'll do better now when I give them a retest. And ordinarily what you might do is just give the retest to the ones that need to improve, right? Because you guys who took it the first time, you've already proved yourself, right? Now I'm going to ask everybody to take the retest because later on we'll use all of the data. So everybody please turn to the retest and go ahead and fill out answers for the retest. Make sure everybody's doing it. Make sure your neighbor's being honest about it. Oh no! Okay. We'll work with that. Like, give me this guy. Well, you can go. Take one like this. I got one first. You might see something a little bit unusual about the solution, the answer choices on this retest, but we'll work with that. We'll work. Where's my hand up? This is my hand. Okay. Okay. Has everybody filled it out? Okay, I'm gonna wait.
Can you, if you have a different, if you accidentally mark something in your research,
Just cross it out or erase it, that's fine. Just as long as you know which one you chose. What you can't do is after I tell you the answer, decide which one you chose. That would be wrong. Don't do that. Okay, is everybody filled out? Okay, so we're going to regrade this. I'm actually only going to ask the people who originally did poorly to tell me what their score is, but everybody's going to grade theirs, and everybody's going to put a score at the top. And we're going to do something with all of them, so you all need to do it, okay? So here we go. Here's the retest key, the retest key. Now my retest has different answers than yours, so I'm going to have to sit here and translate right as we go here, but I think I can do that. Okay. So mark number 1 incorrect if you circled E, the first choice. Mark number 2 incorrect if you circled J, the second choice. Mark number 3 incorrect if you circled M, the first choice. Mark number 4 incorrect if you circled Q, the first choice. Mark number 5 incorrect if you circled V, the second choice. I know this is a little confusing because the letters got mixed up. Is everybody caught up? Okay. Number 6, it's incorrect if you put A. On number 7, it's incorrect if you put D. On number 8, it's incorrect if you put A. Number 9, it's incorrect if you put C. And number 10, it's incorrect if you put A. Okay, so work out your score and put it up at the top. And I'm just going to ask those 3 people, this is the test, this is the retest. Just these 3 people, we want to know if they did better. Brandy, did you do better? You got a 7. Look at that. Okay, who else do we have in the back? What did you get?
A 9.
A 9. Ooh, my reading it.
I got a 9.
Yeah, but you weren't one of those people.
Okay, and then who was the other person? I lost track. Yeah.
I got a 9.
You got a
9.
9. Am I good or what? I have a great remedial program, don't I? And I take these people who don't know what they're doing and look what I have done. I have improved them. And we're going to stop this for a moment. And I told you it wasn't completely serious, and maybe you can tell me why it's not completely serious. And after the break, we're going to have a chance to explain what happened here and what it means. Okay? So I'm just going to let you think about it. Did you do worse? Okay, so think about that. Think about what happened and why this data is behaving this way. Okay? And then let's go back to those assumptions. Or any of these assumptions things that some of you might want to talk about or want to ask a question about? I'm not going to talk about it unless somebody says they want to ask a question. Are those things that you know something about? They're all algebra things, aren't they?
Yep.
Yeah.
They're all algebra things. Anybody want to ask a question? I do answer questions. Oh, yes. Oh, on the retest? That's terrible. Well, she should go to my remediation classes. Your score's really good, doesn't it? Okay. Okay, we ready to go on then? Okay, I'm ready. Turn in your handout to problem number 1. There it is. It's an algebra problem, isn't it? What it says is find the equation of the line that passes through the points 4, 3, and 8, 4. And I very conveniently have given you some graph paper there if you want to use the graph paper. You can plot those 2 points. And what we want to find is the equation of the line that goes through those 2 points. And I'm going to give you a chance to work on that. What does an equation of a line look like? What's that answer going to look like? Yeah, isn't it? Mom knows stuff even though she got only a 6, right? Y equals mx plus b, and your job is to figure out which pieces. Oh, you're working. Work. Oh, by the way, if this is an easy problem for any of you, let me challenge you in this way. I know you can get the answer. Think of as many different kinds of ways that you could go about getting the answer. Okay? If it's an easy problem for you to solve, see how many ways you can list that it could be solved. Methods. I'm going to have Randy come and collect all of your tests. because we're going to actually collect that rest of the data on all the tests and retests to use after the break.
Yeah, maybe the one like that. So we can either, there's two ways to do it. I think kind of a really fast way. We'll just do two. Yeah, just go over. Well, but so if you go from here, pull up to the left, you have to go down. So then if we go 4 over again, you go down 1 again. So
Get the second time. You always pass. What is it?
if we go 4 over here and down 1 over again. That's one way to do it. Yeah, but
Okay, you got an answer? You have an answer? Who else has an answer? Let's do someone in the background here. Who's that?
Okay, I got y equals 1 over 4x plus 2.
Okay, I'm gonna write that down. Y equals 1 over 4x plus 2. Did anybody write down an answer that they think is right, but that didn't end up looking exactly like that? Anybody write it down a little bit differently?
What does it say again? Y equals
1/4 x.
That's exactly what I wrote.
Is it just like that, right? Did anyone write it down differently, but they still think they've got the right answer? Because I can think of several other ways it could be written down, yeah.
You can write it in point slope form and standard form.
I'm sorry, I didn't quite hear.
Point slope form and standard form.
Okay, so which form is this?
That's slope intercept.
slope intercept.
So can you tell me a different way we could write it?
Yeah, it's y equals x. Wait, sorry. Y equals 1/4 x plus 4 minus 4 plus 3.
I got stuck. I just didn't hear what you said.
Y equals 1/4 times x minus 4 plus 3.
Oh, yeah. Is that the same thing?
Yeah.
Yeah, it's just a different form, but if you actually work this out, you have to do a little algebra on this, it would turn into that, wouldn't it? So they're the same line. Okay, well, let me back up here, because you guys probably plotted these, but I haven't. Let me plot mine. There's 4, 3, 4, 3, and then 8, 4. 8, 4. And so did anybody use this method where they actually plotted them and just drew the line in? Is that how you did it? That would be one way to do it, right? So you could just plot the points and then observe the slope and the y-intercept.
I did the rise over 1 and find out how
What did you do?
then I used the rise over 1. Then I
Okay, so find, let me write this down, Joshua. Find the slope, and what you did to do that was rise over run, right?
rise 1 and then move it forward.
And then what did you do after you found the slope?
Then I took the slope that brought in, y equals 1/4 x. Then I did a little back.
So So then you use the graph to look at it. So you used a combination of this and this.
Yeah.
Okay, anybody else have another method that they can think of that one could use to solve a problem like this? Observing where the y-intercept is worked pretty good on this problem, but I could probably give you points where it would be pretty hard to tell where it hits. Or I could put them way far away from the y-axis, and then it would be hard to do that, right? So can people think of other ways? I want to write down a few more ways. What do you got?
You could get the slope as rise over run, and then, so that would be m, and then you can figure out b by plugging in one of the points.
So you could just say, well, I know my equation is y equals mx plus b, and now I've decided that my slope is 1/4, because I use rise over run, and, oops, I'm going to write that. I don't know what b is, but I do know a specific x and y. For example, I know that x could be 4, use my scribbling, and y could be, when x is 4, y is 3, and then I can solve this for b, right?
Yes.
So that would be an algebraic way of solving this, right? I have one more in mind. Anybody have another one? Yeah, one back there.
You could also write it as x minus 4y is equal to -8.
Yes, you could. So back up here, we could write x minus 4y equals, did you say -8?
Yeah.
So that's another way that that answer could look, but it's the same as all of these, right? Here's the way I was thinking of. What if we said, it's kind of went with this idea that we know the solution is y equals mx plus b, and we actually know that this point has to solve that, and this point has to solve that. So I can put this point in, well, that's x is 4 and y is 3, and I can put that point in, and that's x is 8 and y is 4, and then I can leave the m as a variable, and I can leave the b as a variable. Can I do something with that would help me to solve this problem? That's just some algebra, right? Isn't that a system of equations? That's 2 equations, right? How many unknowns? 2 unknowns. That's good, right? When you have the same number of equations as unknowns, and you can solve it. So that would be another way to solve this, right? If you want to get really fancy, you could turn it into matrices to do it, right? So I made a big list of all the ways I could do to solve this. I'm not going to show it to you, but if you're interested in coming up and looking at it later, I came up with 5 ways or 7 ways, depending on how you count my list here. There's a lot of ways you could solve this, and the biggest point I want you to get out of this is it doesn't matter how you solve it. No matter what, you get the same answer. These aren't different answers, are they? They're the same answer. We all agree on that? There's only one line that goes between those 2 points. That's not really what this presentation is about. That's not statistics. That's not a problem. There's not too much information. There's exactly the right amount of information to find a line between those points. It's problem number 2 that's really what this presentation is about. So if you could turn to problem number 2. I'll turn to problem number 2. Oh, look at that. Here it says find the equation of the line, and I didn't say the line. I said a line that represents the linear trend of the points. 3, 2. I added a point. That's all I did. 4, 3, and 8, 4. Look at those 3 points that I gave you. Do those 3 points fall on one line? They don't, do they? So there's not one single answer to this. It's kind of a tough problem because I'm not going to be able to actually find the line. I'm going to find a line that gets kind of close. But if you look at them, aren't they kind of along the line? Like you can imagine there'd be a line there that would represent those points. But it's not going to be perfect, right? It's going to miss a little bit. Now, maybe in your math classes, you've actually drawn in the line, and people call it the line of best fit. Don't do that. Okay, that's against the rules in this presentation. Here's what I need you to do, and this I'm going to give you a little bit of time to talk to your neighbor and come up with a system. I want you to come up with a system for choosing a line that would represent those 3 points, but it has to be numerical. It has to be something that you can do numerically with those points. In other words, just looking at it and drawing it in is kind of wishy-washy. Two different people would draw a different line a little bit, right? I needed to come up with a system so that if you then told your system to someone else, they follow the system, they would get the same answer as you did. So we have that kind of consistency. We like math to have that kind of consistency. Okay? So come up with something to do with these numbers. But before I set you off doing that, I just want to kind of describe the problem, the issue here again. I actually worked out the equations of 3 different lines. What I did was I took each pair of points in those 3. Do you see what I did? And I went ahead and I found the line between them. And you can see I've got them written up there, so you can see what those 3 lines would be. And none of them are really quite right to represent all 3 all at once, are they? I also showed what it would look like if I tried to set up a system of equations to do these 3 points. How many equations do I end up with? 3. How many unknowns? 2. Can you solve that? Is there an exact solution? No, it's too much information. It's kind of a problem, right? So it's a perfectly reasonable thing to say, I'd like to talk about the trend of these points. I'd like to have a model that represents how these points are laid out there. But it's going to have some error. It's not going to be perfect. And I need some system to do it. It's a much harder problem. And with that, I ask you to work on that much harder problem. I want a numerical plan that any person could follow on how you might decide on a line to represent more than 2 points.
So how would you solve it? Thinking? So is this a curved line or a straight line?
That is linear. So where?
Well, I don't know how linear trend are, so.
It's straight line.
Okay. We want it to exist. You said so long. It's actually really great. I don't know what a linear trend of points is.
It's straight.
Is that what you probably? You can probably come up with the way. So you want the line to go around with this. Don't worry about what you think she's going to say. What do you think the line of that that she can use?
Who thinks they have a system that would work, decent system for coming up with a line? What do you got?
I have a question. What's the linear trend?
Oh, what does the word linear mean?
Straight.
Yeah, like a line. So we're trying to find a line.
Find a straight line.
Right, a straight line that would represent, right, because if we were allowed to use a curved line, we could get it exactly right, right?
We can get a parabola.
Right, we could get a parabola with it. So that's why it's this linear trend. The idea is we're going to find the straight line trend of these 3 points. That's a really
Okay.
good question. What do you got?
Well, it's kind of boring. It could always just average all the slopes and average all the lines.
I don't think that's boring at all. Okay, so the idea is you've got these 3 possible lines that maybe are all in some way, each of them represents 2 of the points, right? And each of them has a slope, and so you could take your 3 slopes and you could average them. And then you could do the same with the 3 y-intercepts, and I actually know what the answer, if you do that, I actually know what line you get. I worked that out once. You get the line y equals 0.55x plus 0.6. Yeah. And I don't think I think that's a pretty smart idea, because what you're doing, if you think about, when you say you're taking an average, let's say something about that. What are you doing when you take an average? What is that? Right, so you have 3 things, right? You have 3 slopes, or you have, I don't know, 30 tests, right? And you want to somehow find one number to represent all of them. And when you want to do that, one way to do that is to find the average, which we also sometimes call the mean. And we add all of them up and then divide by the number that it is. And that average number represents something about what the tests were like. It doesn't represent everything, right? But it's sort of in the middle, right? So I don't think that's unusual at all. In fact, an average is a way that we manage numbers when we have more than we need. 10 people took a test, but I just want to tell you, on average, they did this. I want to give you one number to represent it, and that's what I do. I take an average. So an average is one of those solutions to that too much information thing. Okay? So that was an interesting idea. I think that would come up with a line that would be quite reasonable to answer this question. Who has a different idea? Again, I'm trying to find a bunch of ideas. Dustin.
And this is just slightly different. I took the average of all the slopes and had the line go through the mean of the 3 points.
The mean of,
like add up coordinate-wise and divide by 3.
oh. So what you did was you found a point. I'm going to use some symbols here. The average of all of those 3 x values and the average or the mean of all the y values, and you found this point. And then you took the slope just like she did and just found the average slope. So you used that slope and this point, and that's how you found your line. That would work. I'm sure that would make a reasonable line. Okay, we're trying to find as many ideas as possible. So I
Can you
want
repeat what you said? You took the average of all the x's and all that y.
Right. So what are the x's? There are 3, 4, and 8. So we found an average between them. Well, what are they on average? What are those x values? And that's what he used for the x coordinate of his point, and then the average of all 3 y's, and that's what he used for the y coordinate. So he made sure his point went through this. He made sure his line went through this point, and then he used the average slope to pick the slope. That would work, and anybody could do that, right? And you could do it with any number of points I gave you. Anybody could follow that procedure, and the 2 people following the procedure would get the same answer, which we like. We like in math to have a system. We like to have problems that have one unique answer that everyone can agree on. It's really quite troublesome when that doesn't happen. So it makes the mathematicians happy. I still want some more ideas. Yes?
Do we have to use that data, or can we get?
Oh, no, you could use something else.
Can we
Like, Dustin used the averages of the x's and the average of the y's, and those aren't up there.
Right, but I'm saying if those are data points, we'll get some more data.
Yeah, well, that's partly the nature of this problem. The problem is, I mean, I picked the 3 points for an example, but the point is, we would want a procedure that you could use no matter which 3 points I gave you, or if I happen to give you 4, 5, or 6 points, or if I gave you 150 points, you should still be able to follow that procedure. Otherwise, it's not very useful to mathematicians if we can't continue to use the procedure. So that's kind of the idea. We need procedures that would work for everyone. I want to give anybody who has an idea a chance before I talk about some of my ideas. Anybody else have one? Yes?
Okay. Find the line that minimizes distance from each of the points to that line.
Okay. And I want to, that's a sort of a whole nother ballpark in some sense, because what has been happening in these 2 examples that have been given so far is that you've used some kind of averaging or mean or something to find 2 pieces of information. So you've recognized that when you're trying to find a line, there's really 2 pieces of information. You need the slope and the y-intercept, or the slope and a point. There's 2 things. And so far, everybody's procedure has said, I'm going to use this method to find the slope, and I'm going to use this method to find the other piece of information I need. Your method isn't like that, is it? It's going to treat the line as one thing. And you're going to find the line that, say again what you wanted to do?
Minimizes average distance from each of the points to the line.
Minimizes the distance of each point from the line. So let's think about what that would mean. I like this. I have a picture of that, because I anticipated that someone might come up with that very solution. Let's find it. Look at that. There's my 3 points, you see them? And then I've drawn a line in there. I don't know if that's the right line. I just drew a line. And then each point I worked out the distance from the point to the line. And so the idea would be to try every line you could possibly put in there, right? And pick the one that made these distances, the sum of all those distances, the smallest. Would that make sense? Isn't that kind of what you try to do with your eyes when you try to put the thing in there? So you're kind of taking the thing we do with our eyes and saying, we could maybe do that mathematically. And you absolutely can. But this is actually not, oh see, I'm so used to, this is so funny. I'm such a teacher, I'm so used to overheads. I put that underneath there to cover it, and I just couldn't cover it. Okay. So, you can absolutely do this mathematically. And I'm going to tell you why it's not the way we want to solve the problem exactly. It's an optimization solution. In other words, I'm minimizing something. Okay? But it's not exactly how we want to solve it, and that's a good thing, because it's actually kind of a funky formula. I also wrote down all my ideas of all the ways to solve number 2. They're on the back of this, so if anyone's interested in seeing all my ideas on how this could be solved, you could come up with, I made a few of these. You could pick up a list of my solutions. Well, that one, the formula for finding that distance is kind of funky. It's not really very friendly. It's got an absolute value, and absolute value is hard to work with. But it's good. It's not a problem, because we really don't want to solve it this way, and let me tell you why. Here's why this isn't the way we really want to solve it. If I was doing this in the real world, wouldn't X represent something? Something I was measuring, right? It would be some measurement or something. It would have some units that would go down here, wouldn't it? And Y would have some units that go down here, and they probably wouldn't be the same units, because I would be comparing, I don't know, heights to intelligence, or, I'd be measuring 2 different things. And my question about finding this linear trend is to see if there's some kind of relationship. So the smarter you are, the taller you are, I don't know. Maybe that would be true, right? Something like that. But you see that this distance here, right here, see this distance here? It doesn't really mean anything. What units would it have? Because it cuts across both, it has a little bit that's part of X, right, and a little bit that's part of Y, and we have goofy units. And it probably wouldn't have any real meaning in the problem. So lucky us, we don't have to use that complicated formula with the absolute value in it, because it really doesn't make sense to do that, for it to mean something about the data we took. So we don't have to do it that way. So instead, what we can do is we can do our distances just along one of the units. And that's the other picture here. So if I do my distance to the line, not to make a right angle, but rather how far off am I in this direction, this y direction, my formula gets easier. And it also makes more sense because that actually has a meaning. It's an error. It's how far off your line is your model, and how far away the actual points are from the line is what we call error or a residual. It's how far off you are. How much did you miss by? Okay, so that actually means something. It would have units and everything, wouldn't it? So that's a reasonable way to do it. But I'm going to tell you why we don't do it that way, too. That formula's not as bad, and it has a meaning. It's a residual, but it still has an absolute value in it. Can you see why it would? Because here, if you subtract the two, you get a positive, right? And here, if you subtract the two, you get a negative. And you don't want to minimize, you don't want to add the positive and the negative to make them cancel each other out. You want to get as close as possible to all of them, and you want the negative distances to count positively, right? And so you can see why there'd be an absolute value in that. And so you got to add up a bunch of things with absolute value in them, and then find the minimum. And if any of you have ever done algebra problems with absolute value in them, they're terrible, aren't they? Every absolute value, what happens, has two cases, right? It could be positive, it could be negative. The thing could split forever. If you had even 5 points, it would be a disaster to try and figure out. Do you see the problem? It's not pretty. Not pretty. So mathematicians don't really want to do that, even though that would make a lot of sense. That might make a lot of sense. It's a hard problem to solve. So who knows what we actually do? Just fix that absolute value problem. Who knows the answer, what we do?
Square it on.
You square it, right? You square it, then you don't have the absolute value, because a square automatically turns everything positive. And that's a problem that's really very manageable. And that's how we find regression lines. And if you have worked with numbers before, and maybe you've worked with a graphing calculator and things, you know that there's a mathematical way to find a regression line that shows the linear trend of the data. And this is how it's done, and it's called least squares. And what's on this handout here is the square. You see there in yellow. So what you do is you take this distance and you square it. And so it would be the area here, and the area here, and the area here. And again, you're taking that line in there and you're wiggling it around, and you're finding the sweet spot where the area is the smallest it could ever be. And the beautiful thing about that problem, which unlike the absolute value problem, there's always one unique solution. And mathematicians like that a lot too. So that's the way that these problems are solved. And I want to show you one more thing about it. We're going to take a break in just a moment. What happens as soon as you move from measuring on y here to get it using the residuals is something that a lot of people don't realize. This picture here is set up so that if you tell me what x is, I'm going to use this model, this line here, to predict what I think y would come out to be. And then I'm going to be off by the residual. Okay? Do you see that if I were to do it the other way around, and this is why I put this on an overhead, if I did it the other way around, I'd get completely different distances, wouldn't I? Because I'd be measuring on x. You don't get the same regression line if you switch x and y around. It's a little bit different. A lot of people don't know that. Because the natural thing to do once you get that regression line is to try it both ways. Let me give you x, and now I'll use the regression line to predict y. Now I'm going to give you a y, use the regression line to predict x. And books will do that, teachers will do that, and it makes a lot of sense. But it's really only valid if you have a strong relationship. If you have a high correlation value, r equals 0.9 or something like that. If r is not great, then those lines are really very different. So what a lot of people don't know is that these regression lines are one directional. And the reason they're one directional in part is because you're doing these, you're calculating, I can't get it right. You're calculating these differences on just one of the variables here. And so if you switch it around, it would be different. The other reason why they're different has to do with the explanation of what was happening with the data here. So what I want to do is I want to take a break. After the break, we've got 3 things we're going to do. We're going to talk about the data and what was happening with this and what the explanation was. And I want you to kind of think about that, because the explanation for what was happening here has to do with what I just said about the regression line and it being a one-directional thing. So I want you to think about that, and we'll talk about that first thing when we get back. And then what we're going to do, we can't actually solve the least squares problem. It's a hard problem. Not there. Remember when I set up the system of equations? How many variables were there? 2. Okay? There were 2 variables. And it's an optimization problem. You're trying to minimize the squares of the distances. An optimization problem is usually solved using calculus. So you actually need multivariable calculus to solve that problem. It's not a hard solution. It really isn't. People who haven't seen it think it's hard. It's not. It's a pretty simple multivariable calculus solution. I actually have it written here if anyone wants to come look at that solution. But it's something that we can't do because we're not going to do multivariable calculus. But I do have 2 least square problems that all of us can solve, just using algebra. Okay? We're going to do those 2 least square problems after the break. Okay? And that's all I have. Is there any questions? Okay, so we'll come back in about 10 minutes after.
What was that for? Being Rosie? Being Rosie? What's that about? It's not about being
This is and people don't realize it because it's scary. It's got summation lines in it. It's not hard. I'm going to make, look what I'm doing. I'm making a graph, and I'm showing you past 1.
We were actually at A&M Physics for the last 7 Saturdays, so you can come to me. But yeah.
We'll look at it after.
The test average score was 8.
Did you want to look here?
Yeah, okay. That's very still. And I'm
Yeah,
Oh, okay.
Good. Looks like a pretty hard test.
Josh was a little concerned about that. He's like, what do I do now? You never had a test with no questions, right? And then you were upset you got 2 wrong.
luckily I got.
I got
So wait,
6
how was
wrong.
the scores going to decide if there were no questions?
because there was only one way to do that. So there's
Oh, I see. Okay.
7.5.
All right.
But you gotta, shouldn't make it too scary. Okay, remember before the break how I was talking about how us mathematicians like to solve this linear trend problem using least squares and not least absolute values? What did I say was wrong with least absolute values?
Ugly.
They're hard to work with. They're really hard to work with. And the one thing I said about least squares is that when you do the least squares problems, you get one unique solution. And that's not true of the least absolute value problem. You can do it, but sometimes you can set up your points in such a way that there are bunches of lines that all have the minimum. And thanks. And because of that, the solutions aren't stable. And there's a really neat applet, and I've got the URL for this on the back at the end of the handout there. And I want you to see it, and it's so neat to do. Over here, the problem is working out a least squares line. You see this, all the little squares on here? See there? That's least squares. And over here, they're doing least absolute value. And you've got the same set of points on both sides. So I can move these points around and see what happens to the least squares solution and the least absolute value. And what should happen if I do this is that you'll see that this thing on this side always moves around. Now watch it won't work. So you have to do it here. Okay. On this side, on the square side, the line always moves around smoothly. On the absolute value side, see you see it jump? So somewhere right in there, there's this sweet spot where there's a ton of solutions, where there's all those lines from there to there from that jump all work. That's not very nice. We don't like that, us mathematicians. We don't like multiple solutions. We want there to be one solution so that everyone will get the same thing. And we don't like this, the way this jumps around. It's hard to work with. So you could solve it that way and it makes some sense, but it's a really hard math problem and it's not very convenient in all sorts of interesting ways. So that's an interesting effort. Okay, I said we were talking about the data. Do I have someone who wants to try and explain what happened? Remember what happened was we had 3 people who had not so great scores, and after I talked to them, they took the retest, and their scores improved. I've lost where they improved to. They improved to 9 and what? 9 and 7 and something else. 9. Okay, so those are better. So these 3 scores all went up, and I said, isn't that great? I gave them good advice, and they did better. So does someone want to help explain what happened and why it happened?
I know, it looks like a Gaussian curve for me on both tests.
What's a Gaussian curve?
Bell curve?
A bell curve, right? It kind of has a hook in the middle, right? I mean, like that. Yeah, it does, doesn't it? So mostly people get what scores?
7 and 8.
7 and 8, right? Can we explain why they mostly get 7 and 8? I mean, was that a surprise? Think about how I made that test, yeah?
I think they get 7 and 8s because there's always a quarter chance that you'll get it wrong.
Mm-hmm.
And since therefore there's a 3/4 or 75%
Mm-hmm.
that you'll get it right.
Right, so the chances of getting it right are 75%.
Yeah.
So if that happened exactly that way, what would the score be on the test?
Well, 7 or 8.
7.5, which we really can't. Nobody can get 7.5, right? But 7.5 is what we call the expected value of this distribution. It's really the mean. It's the thing that we'd expect most people to get. Now they don't all get that, right? They get lots of different things, but we expect it to be centered around this number right here. Good, excellent. Nobody's telling me why they think these guys improved. Anyone have anything to say about that? Go.
I think he gives them like the answers.
Is that what I did? Who did I talk to? Did I give you the answers? I kind of gave them the answer. I gave them the answer to why this happened. I didn't give them the answers. Anybody else have any theories? Yeah.
You may have done was they just choose the same answer for each problem.
I initially didn't give them any tips about how to
Okay,
fill out their
it's
thing.
single random.
I didn't give them any information about how to take the test. They had no advantage over everybody else that I gave them. And yet, the way I presented it to you all, it looked like I had given them help, didn't it? So my question is, how come it looked like I gave them help when I didn't give them any help? Yeah.
I think it's because it's just so random and, well, they were on the, it was a greater probability that they would get a better score.
What's your name? Paul, I remember. Did you hear what Paul said? The chances of being down here aren't really big, are they? The probability of being down here is 3, at least about 3 out of however many people took the test, right? That's what it looks like according to this, right?
It's pretty cool.
So the chances of being down there aren't that great. So if I send them back to do it again, they're most likely to get what? 7s or 8s, because that's what everybody's most likely to get. Does that make sense? Who remembers what I said to you guys, the ones that came out and saw me? Do you remember what I said to you? I did say something. You don't remember. Who was, the other person's not here. I said, what I want you to do is regress towards the mean. What do you think that means?
Oh.
Anybody have any thoughts? Go ahead.
Like get more toward the average of what's expected.
Right, you're going to become more normal, more regular. You think that's something you have to work at doing? No, it's just something that happens. Right? It's a phenomenon. It's not a tip that I gave them. It's a phenomenon. It's something that happens. If I happen to pick all the people who are unusual in some way, either because they got an unusual score on this test, or I picked all the people who were the tallest, or I picked all the people who were somethingists, right? If I pick the unusual people, the people who are at the extremes of all the things that could be true, so they're at the tail of our distribution, and then I go and I measure something else about them, or I just remeasure what I already tried to measure, they're most likely to be less extreme the second time around. Because what the phenomena is that they're going to regress towards their mean. People being on the extreme is unusual. And if you happen to be on the extreme, you might be on the extreme because you're extreme. You might be extremely smart, which means you're going to be extremely smart all your life. But part of, when I try to measure how smart you are, part of what I measure is how smart you are, and part of it is some randomness, right? And that randomness happens to be, when that randomness happens to go in your favor and make you look smarter, well, the next time I measure you, you're not going to look quite so smart, most likely. Okay? That's regression towards the mean. And that's a really important phenomenon to understand, because people can do experiments like the one I did, and they can say, look, I've created this remedial program, and look, everybody improves. Well, of course everyone improves, because you started with a bunch of people who already were doing, started with people who were doing the worst. Now, this test isn't a perfect example in the sense that this test was completely random, right? And most tests would be about something, and they would actually measure something real. Like I could have tested you on, I'm trying to think of something I know nothing about, Saturday morning cartoons, right? I could give you 2 tests on Saturday morning cartoons. And if you know a lot about Saturday morning cartoons, you probably do well on both tests. And if you don't know any very much, you probably do poorly on both tests. So there'd be some correlation. The people who did poorly the first time would be more likely to do poorly the second time. But it wouldn't all be that. It wouldn't be perfect. It wouldn't be all along a straight line. Like if you got 3 on the first one, you'd get 3 on the second one, because I wouldn't ask the same questions or whatever. And so there'd be some variation. And that variation is the thing that regresses towards the mean. The randomness, when the randomness part comes out unusual one time, the next time it's like you're more likely to be more average, and you're more likely to be regress towards the mean. Does that make sense? Does anyone have any comments about that? Okay, here's what I want to do. I want to make a point, and I'm not sure if I'm going to use this to make it, but let's look at this first. So I put the data here, and we can see that the 2 tests don't look very different. And if by chance I were to take the 3 people who did poorly on the retest, where do you think their scores would be here? Well, obviously they're not down here, right? Because we know they weren't. They're somewhere up here. So these people who took the test the second time and were unusual the second time regressed towards the mean of how they did the first time, right? It works both directions. Okay. This is the reason, regression towards the mean is the reason why you need to have a control in an experiment. Because if I take people who are sick, unusually sick, and I try to impose a treatment on them, if I've taken a bunch of people who are sick, they're likely to get better. And it might not have anything to do with my treatment. So I have to take a bunch of people who are just as sick and I have to not give them the treatment. I have to see that the ones that got the treatment improve more than these guys. Otherwise, regression toward the mean will make it look like my treatment is effective when it's not. Same for testing and anything like that where you're trying to measure the effect of something. You've got to be really careful about the regression toward the mean. You hear it in sports too all the time. You hear that when somebody, I'm not a sports person, so I can't talk about this like I know about it, because I don't. But like when somebody gets recognition for being really good one year in some sport or something, then the next year they're bound not to be as good, and they think of it like it's a jinx. Well, it's not a jinx. They got the recognition for being unusually exceptional, and so the next year they're not as likely to be exceptional because of some of the exceptional is how good they are at the sport, and some of it is that they were lucky that year, right? And so that's a phenomenon that's pretty typical. It's also why your parents might think, you might want to talk to your parents about this. It's also why your parents might think that scolding you works and praising you doesn't. Think about this. Because if you kind of screw up, which I assume is unusual, that you don't usually screw up, and they scold you, then probably you're not going to screw up the next time because it's unusual for you to screw up, right? So you probably will improve. But if you do something like really exceptional and they praise you for it, probably you're going to be kind of more ordinary right after that. And they'll think, well, my praise doesn't work, but my scolding does. But it's not that at all, right? It's just because you're more likely to be kind of ordinary than you are to be at those extremes, right? So you might want to cue your parents. Okay. This is what I'm going to look at. Here's my graph of the data. I don't want to run out of time. Here's my graph of the data. Here I've got on the x-axis all the scores for the first test. And here on the y-axis I've got all the scores for the second test. And this is kind of a tricky question, but I think it's something we should mention. Somebody sort of already talked about it a little bit, because we talked about what scores were expected on these, right? What if that was all my points and I was trying to find a regression line to represent them? What should the regression line for these points be? Do you think there is one? Is there a linear trend? Should there be a linear trend? Anybody have anything? Let me ask this question. Is there any relationship between how you did on this test and how you did on that test? No, it was random, right? I didn't test anything real so that there would be a correlation, right? So if I tell you what's on the first test, do you have what's your prediction of the second test? What's your best guess? Someone already said.
7.5.
7.5, right? My best guess is how you're going to do on the second test is 7.5. It doesn't change if I know the first test. So my regression line, it's good to kind of get used to thinking about regression lines this way. They're all about prediction. If I know what I got on the first test, it doesn't change what I think you're going to get on the retest, which means the regression line that we expect from data like this is perfectly flat around 7.5, just like that. And that means there's no correlation. It means that how you did on test 1 doesn't have any bearing on the prediction someone will make for test 2. Now, the other point I want to make, and I thought I would make it with this, and I'm not sure this graph is quite useful, so try and use the board. Ordinarily, you expect data to look like this. You expect there to be maybe some relationship, right? So you expect maybe something like that, right? So there is some relationship. If you just eye the relationship in here, you might get that. What do you suppose that phenomena of regression to the mean does to that line? Where's the mean of the thing I'm trying to predict? Somewhere here, right? So if my prediction is going to regress towards the mean, what happens is the line that I use to predict this is instead of being right through here, it's a little bit shallower. And that's why, that's what I was talking about, the regression line being one direction. Mostly, often, it doesn't matter. If it's very highly correlated, you can use it both directions because this wiggle, there's not that very much wiggle within the data, so you can go both directions. But it's kind of, it's something to know that it's a one-way relationship. Okay. Are there any questions about that? We have two problems to solve. Look at problem 3. And I'm going to close these up. I'm going to look on the board. My handout. Problem number 3. Here we go. Oh, I need 3 volunteers. Raise your hand. What did you get on your first test?
I
Do you remember? Which one? Pick one.
8.
8. Okay, so we got 8. Another volunteer. Right there.
We got 8.
Only a piece. Sorry.
9.
You got-
on
you
my
got a 9?
second test,
Okay, we're gonna
but
go-
I got 8 on my
We're
third.
going to go with 9. And I need one more volunteer. Someone didn't get an 8 or a 9. Yeah. I don't like that. 4. 4. Let's go with 4. That's better. A little more spread. Okay. So you can fill in those numbers on problem number 3. Okay. And so what we're going to do is we're going to do a least square problem. But we're not going to do the one that I've been talking about because it has 2 variables and we use calculus. So we're going to do this one. And you might guess what the answer is before we even get to it. So you can think about that. What we're going to do is we're going to take these 3 numbers and we're going to try and find a number that represents the 3 numbers pretty well. And the way we're going to find the number is we're going to find the number whose square of the distance from each of the numbers is a minimum. That's a least square problem, right? We're going to use least squares. Okay? So let's set up this problem. Okay, so if I want the difference between, let's call the number that I'm going to use to represent these x. Okay, we use a variable. And then let's say that we want the difference between x and 4, so that's the difference between x and 4, and I want to square it. And then I'm going to add that to the difference between x and 8, and I'm going to square it. And I'm going to add that to the distance between x and 9, and I'm going to square it. And that's going to come up to some sum, we'll call it x. Okay? Now, what are we trying to do with s? We want a particular x, the one that does what? Makes this as small as possible, right? Okay, now I claim that we can do this without calculus. I think we can. First of all, let me ask you this. Does it matter which direction I do these subtractions in? Could I have done 4 minus x? Why? Why could I subtract either way? I'm squaring it, right? So if I square a negative, it's positive. If I square it, right? See, this is. You can see right now why absolute values would be just terrible to try and solve. But this isn't so bad because we know this is a positive number, and we know it's going to have a minimum. Well, how come I know this has a minimum? What kind of function is this? If I were to try and graph that, what would that look like? What is that? It's a parabola. How do you know that? I think we better kind of manipulate it. What would we do to this? Try to open it up here. What would we do here? Can we multiply this out and get 3 terms and can multiply that? Know how to do that? Okay, I'm going to let you just work on that for just a second. I don't want to get ahead of you. all these other guys, plus, what happens here? Somebody else? Yeah,
X squared minus 16x plus 64.
plus 64, okay, good. And then somebody else, will do this one? And what's this one? Don't make me call on my son, because I know he knows.
X squared minus 18x.
Minus 18x.
The constant term doesn't matter.
No, look, we're gonna write that.
Right, 81.
Okay, and now we can actually combine all three of these x squareds, right? There's three of them, so it's gonna be 3x squared, and we can combine
I already figured out the answer.
x. Have you already figured out? You know what this
I
is?
started middle.
Did you work out minus 8, minus 16, minus 18?
I already did.
I'm trying to save time here. Who's added those three up for me? Let's see. It's gonna
I
be-
got
Is it 42?
yeah.
10, 20.
So
I'm so confused. What is it?
Yes, it's 42.
Wait,
It's negative 42.
Minus cos 2x plus 1.
And then we add up the end, and what is the end? 16,
16.
8. See, I should have lined them up this way, right? It would be so much easier for me to do.
161.
Thank you, I appreciate it. Okay, and if anybody thinks that's wrong, we'll fix it up. I promise you, just check the work. Okay, so now that's looking like what we should be a parabola, right? That's a quadratic. Does that open up or down? Opens up because it's got a positive in front of the x squared, so it's a parabola, looks like this, and guess what a parabola has? It has a minimum, right? And the minimum is the vertex, and now you see why I put on the assumptions that I wanted you to be able to find the vertex of a parabola. How are we going to find the vertex of this parabola? I'm looking at my little handout here. I remember way back here at the beginning, I said, finding the vertex of a parabola, and this was the example I gave. And nobody asked any questions, so I guess that means you know how to find the vertex of that parabola. What is it? What's the vertex of this one? What?
3x squared plus 30 plus 15.
Well, see, but you're going to turn this equation into this, right? Here's what I want to know. If I graph that, it's going to look like that. I want to know what that point is. That has a point, right? What is it?
Minus 5.
It's minus 5, and on this one, minus 10. Okay, because this is called, this form here, this is called the vertex form. It's really easy to pull the vertex out, right? So this isn't in that form, is it? So we have to put this in that form, and then we can find the minimum. That sound like a plan? I think we should do it. So to get it in that form, see that 3? I'm going to keep that 3 out here on the outside, just like this. X squared minus, now what happens when I factor 3 out of that? Won't this be 42 divided by 3? Because if I multiply 3 times that, I have to get that. And I'm going to leave this plus 161 out here. Okay? And I'm trying to get it to look like that, so let's see. 3, I need this to be x plus or minus something squared, right? And then plus something out here. So what do I have to put inside of here to get this to factor into that? And now, if you think about it, if you look at what we did, you go from there to there, and from there to there, and from there to there, we're just going backwards, right? So what do I have to do? I have to do what to this? Divide this by 2, right? Because look, when I had a negative 8 here, that was a minus 4. When I have minus 16 here, that's a minus 8. You see? So if I just divide that by 2, let's see, that would be minus let's see, 21, right? Divided by 3, then I should be able to get this to match. I'll just have to add some number. Well, what number would it be? I have to square this, don't I? So it's 21 squared over 3 squared. Now I can figure out what that is, and I can figure out what it is times 3, and then I can go ahead and subtract it off, which is what I really need to do, minus some number that I can figure out. Do I really care what this is? That's the y value of that minimum. Do I care what the minimum of that sum is? No, I know. All I care about is what value of x will make it minimum, right? So I don't really need to do that work. I actually should be able to pull my minimum right out of this. What is it? What's x? What's the number that minimizes this? The value of x that minimizes this. Look at what we did here. When it was plus 5, the number that minimized was minus 5. So if this is minus 21 over 3, what's the number that's going to minimize this sum?
Plus 7.
Plus 7. Let's call, I'm going to keep it 21 over 3. Okay? So it's going to be x equals 21 over 3 minimizes the sum of the squares of the distances. And that's my answer. It's 7, isn't it? Can anyone tell me what that number is? It's got a name.
Yes, 2 names.
What is it? What is 7 to these numbers 4, 8, and 9? Yeah?
It's the mean.
It's the mean, it's the average, right? If I add up 4 and 8, 9, and then divide by 3, don't I get 7? And don't you see that if we did this problem, no matter which 3 numbers we had, or no matter how many numbers we had, wouldn't it always come out that way? Because you always double these, right? And then you divide by 2 here, and then you always divide by however many x squared. Do you see that it's always going to come up to mean? Always. So what people don't maybe realize is that the mean, or the average of a bunch of numbers, is really a least square estimator of those numbers. That's kind of cool, huh? So you've been using least squares all the time. And you just didn't know you were using least squares. Okay, I got one more problem. We've got time to do it. Look at problem number 4. And problem number 4 goes back to the 3 points that we had. And I kind of want to give you a visual. Well, you've got it in front of you, right? You can look at it on your paper. Oh, no, well, let's do this. Let's look at it. Just quick. I'm just going to put one of these screens down for us. Okay. Oh, do I need to turn the lights off so you can see it?
probably better.
This?
Left mark. It's the one with the switches that are.
This.
Yeah.
How about that? Is that better? Okay, so the problem that I gave you that was too hard was how to find the least squares estimator of these 3 points when the solution expected was y equals mx plus b. In other words, I allowed any line to be possible. So what I've done in number 4 is I've restricted the solution. So the solution no longer can be y equal mx plus b. Instead, the solution can be y equals kx. So what am I requiring of that line? It has to go through, what does b have to be? 0, right? So the y-intercept is 0, so it has to go through the origin. Does that make sense? So it's still every line, but it's only every line that happens to go through the origin. I'm requiring this to be a direct relationship. And that's not an unrealistic problem at all. I didn't have to turn this into an unrealistic problem to make a problem that we could do here together. It's a very realistic problem. In fact, I can give you an example of a problem that we might be doing where we would want to do exactly that. What if you were measuring the height of sheets of paper or the thickness of sheets in books and trying to compare that to the number of pages? Wouldn't that have a linear relationship? The thicker it was, the more pages there would be. And what should the answer to that problem be if the thickness is 0? 0 pages, right? So if we would want to model, if we're going to try and make a line that represents that, right? We would want to model that went through 0, 0, wouldn't we? So it's not an unrealistic problem at all. Oftentimes you would have a relationship where you would know if one variable was 0, the other one should be 0 too. And so this is not an unreasonable problem, and lucky for us, it only has one variable. And the other thing, it fits our data. Does that data look like it could have a linear trim that goes through 0, 0? It's not unreasonable. So 1, it fits our data, and 2, it's not an unreasonable question. And now we only have one variable, and we can solve this problem with the techniques that we just used to solve the first one. So we're going to do that. I'm going to turn all the buttons here. Okay. Okay, somebody read out the points, please.
Oh,
3, 2,
4,
4, 3, and 8, 4. Okay. So what do I need to do? I'm going to write down an expression that is the square of the residual, of the square of the difference between my line. My line's going to be y equals kx and the actual value of y. Okay? So my line will tell me that my line here that I'm going to come up with will tell me that the y value is kx. So it would be k times whatever x is, 3. And I want to compare that to what the actual y was for the point. So what's my y here? Oh, there it is. See it? That's 2. So that's my residual. Do you agree? And I'm squaring it. That's the distance along y, the residual, and I'm squaring it. And I'll do that for all of these. So add to that the difference between what the line will tell me, which is k times x, subtract the actual value of y, and square it. And do it here. K times x, subtract the actual value of y, and square it. And that's my sum of all the residuals. The squares of the residuals, squares of the distances. Well, is this kind of like what we had before? What's different about it? I'm going to rewrite it a little bit. 3k minus 2 squared plus 4k minus 3 squared plus 8k minus 4 squared. Okay, so can we do the same thing we did before? Expand these? Okay. What would that expand to? Let you look at it. Okay, 9k squared. The middle's kind of hard, huh? I feel compelled to do a little work to think about this, so I'm going to write what I'm thinking over here. Okay, so I see the 9k squared. Now, where does that middle term come from? What's the middle term? It ends up being minus. Yeah, so it's going to be minus 12k because you're going to get a minus 6 and a minus 6. You see that? That's how you're going to get the middle term and then plus 4. Does that make sense? Okay, this time I'm going to be smart and line them up so I can add them up more easily. Okay? So let's go ahead and expand that one. What's it going to be? 16k squared, and what's the middle term going to be? Minus 12, I'm going to do it twice, so it's minus 24. And then what's the end going to be?
9.
Anybody need help with this, or are we okay? Feel like you know what you're doing? Okay, what about that one? 64k squared.
Minus 64.
There's 4 10 days, 32, and I double, I get 64. Plus 16. And I add all that up, and that's going to be S, so let's add it all up. Okay, let's 6, 10, 20, no, 10, 10, 26, 20, 30, what is it? 89, thank you. You don't get stupider when you're standing in front of the board. If you haven't tried it, you don't know, trust me. What is this, minus what? 100K. And then we add those up and we get 29. And that's my sum of the squares of the residuals. And I have to minimize that, and that is also the graph of the what? Parabola, and it goes up, so therefore it has a minimum, so we say hooray, I can solve this without calculus. All I have to do is find the vertex of the parabola, but I got to get it in this form. So I'll do what I did before. 89 k squared minus, and then in order to take this 89 out, I'm going to make this 100 divided by 89 plus something I'm not sure, and I'll leave the plus 29 out here.
Left out the K.
Oh, I left out the K, thank you. Appreciate that. Okay, and then I have to make this look like that, so 89 times K, and it's going to be minus, what was the pattern last time? We subtracted, whatever this was, we had to take what? Half of it, right?
Yeah.
So it's half of that, so it's going to be 50 over 89. And we should be able to make this into that square. In order to do that, we would have to add 50 squared over 89 squared. And then I could work out that times 90 is, let's see, well, that would be 50 squared over 89, which I've added in here, so I'd have to actually subtract 50 squared over 89 to make this all still equal, but I don't really care what that comes out to be, so that's not that important to solving this problem. So I get that plus something, some number, equals S. And now tell me what value of K minimizes this X. What's the vertex, the X coordinate of the vertex of this parabola? What is it?
50 by 89.
It's 50 divided by 89, right? So my answer to this problem is K equals 50 over 89, or my least square regression line is Y equals 50 over 89 times X. And that line minimizes the squares of the residuals to the points with the requirement that it goes to point 0, 0, it goes to the origin. Okay? We have just time to generalize this. So we will. So that's really nice that we could do that, right? But wouldn't it be cool if we could generalize it so we wouldn't have to do all this work when we were given another 3 points, or 5 points, or 10 points? So let's try to generalize it. Let's see how we got to this. All we need is one number, right? We just need to say where we got that number and see that we would always get the same thing, right? So let's figure out, did I write it down wrong? It's 50. Why did I put 58? Who let me do that? It was you. Okay. So let's see where that 50 came from. Where did the 50 come from? Well, it was 100 here, right? And where did the 100 come from? It was the sum of all of these. Where did those come from? What were those? I picked the harder one. I should have started with 89. It's easier. But we can do this. Where did these numbers, 12, 24, and 64 come from?
We multiplied together the X and Y coordinates.
Right, you multiplied the x and the y coordinate together and doubled it, right? So first you multiply the x and y together, double them, add them all up, and then you divide by 2. So we multiplied by 2 earlier, and then we divide by 2. So that part we could just leave out, right? And what you've really done is you've taken the sum of the products of the x and the y. Do you agree? So this 50 here is the sum. I'm using, let me make this bigger because you might not be familiar with this notation. The sum of x times y. All this means is I'm going to count all the points. I'm going to give them numbers 1 through n. And I'm going to multiply the x times the y, and I'm going to add them all up. That's what this sum means. I could write it out, right, add them all up, but this is a nice shorthand way of writing it. Okay. Divided by, that's the 50. What's the 89? Look at the work over there and tell me where the 89 comes from. Okay, let's see. The 89 was down here. It was out here, right? Isn't that where it started out? It is, isn't it? It was the squares of all the x values. 3 squared, 4 squared, and 8, right? So what we would do is we take the sum of all of the x's squared. And so this is the generalization of how you would come up with k. For any number of points that you have, and for any number of points, as long as your requirement of your least square regression line is that it went through 0, 0. And we solved it without calculus. I have 2 things to say, and then we're going to be done. Can you look at that? It's the slope, right, of the line, right? Isn't it the slope? Can you look at that and see that it looks kind of slopey? Look at it and tell me what's slopey about it. Someone should say, yeah.
Like changing y over changing x.
Yeah, if you just took out one of the x's here, right, you see it's all,
Yeah.
that's all about y, right? And if you took out one of the x's here, now it's all about x. So you can see the y over x, can't you? Isn't that cool? If you look at the back of your handout, the very last page of your handout, I've written the solution to the least squared regression line where it doesn't have to go through the origin. It looks like this. The slope m is the sum of the products of the x and y's minus the number of points you have times the average x times the average y, all divided by the sum of the squares of all of the x's minus the number of points times the average value of x squared. Tell me how this relates to that. Do you see this piece of it? It's just that. So we solved a pretty sophisticated problem, didn't we? We just had to parse the problem down just a tiny bit, so we only had one variable. And then we can solve it without calculus. And we can see how it's similar to the bigger problem. That's all I have. Is there anything, any burning questions or burning issues anyone wants to share? It was lovely to talk to you all.
Yeah, well, thank you.